Windows. Oh, Windows just worked. Didn't see that coming. So Steve and Alex, the handwritten notes are already posted to the website, at least they should be.
Okay.
And I think he's wrong. In all seriousness, I think he's wrong. I think you can offer it at higher price. And I think you can turn it out in the niche market. I don't think he sees that opportunity. I think he's looking at it as the way it is right now.
We paid like $60 for a case
Yeah.
of
Case of what?
capping.
Oh, yeah.
And like they had more of them. They were charging like 150, 300.
I think if you position correctly, someone's not going to.
So if blue runs out, the rest of the class is going to be in pink.
Premium niche.
I haven't read one.
Yeah, do you? If this runs out, I might ask you for it.
You're femininity.
I don't care about the girls, okay? No, it is not. It's more about legibility.
There is that. It's not on the base. It's like in the center of the lower right. Like right here. Over your hand. You can grip the side and you can raise it with your hand. Back a little bit. There. Oh, there.
That was surprisingly hard.
So I was worried we were going to have another snow day. Steve's not going to be here because of snow, apparently.
Where's the
I don't know. He said something
I
about
think it lives
hill
like 2 counties away.
and ice. Okay, all right.
I will say, early this
Acceptable.
morning, it was actually decently snowing, yeah.
Well,
They
there
didn't
was
have
ice
roads
coming
here
down.
till like 9 or 10.
Yeah, I stayed home this morning, mainly because I wanted to wait until the precipitation stopped so I could snowblow my driveway. But hey, I've gotten to use my snowblower twice in as many days. So.
It's gonna start raining, I think.
God, I love that machine.
Does it work?
Oh, yes. Oh, yes. So I spent 2 or 3 winters shoveling our driveway. And we have some of you have been to my house. We have a long driveway that like wraps around. And so it's 2 or 3 times longer than it needs to be, you know, to get a car from the road to the garage. And I would just shovel that thing by hand. And it would take me well over an hour. And, you know, if it snowed like a foot or something, I was just like, okay, well, this is what I'm doing today.
How long does it take with the snowblower?
20 minutes.
With a foot.
Yeah, doesn't matter. The snowblower doesn't care. As long as it doesn't get above 14 inches or so, which is the size of the blade. But come that 3rd or 4th winter, it must have been the 3rd winter, I was griping about this, and it took me forever to clear the driveway. I'm telling my wife, just drive over the snow. We got a 4-wheel drive for a reason. That month, she told me, I bought you a snowblower. You can go to Home Depot and pick it up. It's ready now. And she's like, I don't want to hear it again. We're done. And bless her, she got the biggest one they had. This thing's a machine. And I do so love it. Got an electric start, you plug it in. Shoot snow.
I still never shoveled snow in my life. Putting it off until ever.
You know, it's one of those things you should do at least once.
Not me.
I computed it one time when we got 14 inches of snow. I, estimated the density of the snow and then the size of my driveway, and I moved like well over a ton of snow.
Does it count for good workout?
Yeah, well, I was sweating. I mean, you go out, it's cold, and so you're just dressed up in mittens and all this stuff. And by the end, I'm peeling off layers down to nothing but a t-shirt. Ugh. Ugh. Steam just smoking off my body.
You guys driving by.
Crazy up
Yeah, that's how we do it in Michigan. Okay, let's roll. So today we're going to start with Baumgart-Shapiro. Did y'all read chapter 1 of Baumgart-Shapiro? Or did you forget? I forgot. All right, that's fine. Chapter 1 is pretty straightforward. The biggest stuff, which we're going to talk about in class today, go back and read chapter 1, because there's some stuff that I will not have time to cover today, I think, that you should be aware of. It's really just a review. And a lot of it is a review of the stuff that we've spent the last 4 weeks going over in terms of general relativity. There are some new things which I'm going to introduce today. Not so much new, it's just we didn't talk about them with this language when we were talking about it in Thorne and Blanford. And so I will introduce that language. And some other notational differences that Baumgart-Shapiro used. And then we will introduce the Tolman-Oppenheimer-Volkov equations for stellar structure and GR. I have some notes then on Oppenheimer-Schneider collapse, which we might get to, or we might not. We'll see if we have time. But that just basically is the collapse of some hydrostatic star to a black hole, which is kind of cool, right? You can draw this space-time diagram of the emergence of the event horizon and talk about what that means in terms of space-time diagrams and the equations. And it's one of the few useful analytic solutions to the field equations, which is kind of nice. Okay, questions before we get going? The other thing is that I've posted now to the website our midterm project. And like I already said, it's going to be solving the TOV equations numerically for the hydrostatic structure of a neutron star. So I fleshed that out a little bit. I've got some notes. One of the reasons why I don't think we'll get to OS collapse today is that if there is extra time at the end, I'd like to go over that a little bit in detail so that we all know what we want to do. It shouldn't be too much work. It should be kind of fun to implement a solver for the TOV equations. And I do think if you do it in Python, you can basically import, NumPy's ODE solver and you're done, pretty much. I did add a wrinkle to it, which was the easy way to do it, which is what I want you to do at first, is to assume a polytropic equation of state, which is just analytic expression. But then what I want you to do is extend it so that you can input arbitrary equation of state tables from a website I'll show you. And then the only work in that will be reading in the HDF5 tables and doing a little bit of interpolation in them. Again, 10 lines of Python if you want to do it in Python. But I also have example code that I can point you to in both C++ and Fortran if you want to do it in one of those lower level languages. But we'll talk about that hopefully at the end of class, but I'm going to raise that now. It's up on the website. Maybe I'll plug in and show it to you at the end of class. Okay? All right. So, onward. Now let's get numerical. Also, I pushed back the due date for homeworks 1 through 4. I'm not going to assign a homework for this week. You're welcome. But do take a look at the project. Start looking at the project because the homeworks are going to come again. There are a lot of problems in Baumgart-Shapiro as you start reading through. There's none in chapter 1 because it's just a review chapter. But once you get to chapters 2 and on, there are a lot of problems, like 50 per chapter. I toyed with the idea of making you do all of them. But if you just read through them, most of the solutions, like most of the results from those problems are important and you should know. They're not just toy problems. They're like derive this. They're like show that this equation has this property. And so they're things that you should know. So read the problems. And for the vast majority of them, at least the ones that I've looked at, you can look at it and it's very simple and you can know what to do, right? You know, oh, I see what they're getting at there. And I know how I would attack that problem. And so I'm not going to assign those problems, but do read them when you're looking through the chapter. And then I'll pick out roughly 5 problems a week again to do
once we get going, but not this week. Not this week. All right. So Baumgart and Shapiro, they use geometrized units throughout. Okay, we had this already in Thorne and Blandford. Question? Yeah. Oh, when is it? That's a great question. I forgot. Schedule. I put next week, a week from today. Is that long enough? Yeah, Tuesday, a week from today, the 19th. And somebody has all the solutions. I hope
Nate Bodie.
Nate Bodie. Okay, so go get them. I just work out the problems. I don't care if you get the solutions. I printed them out to show, to help Mike with one of the problems, and I was like, here you go.
Sorry, my desk. I take pictures
That's just for homework 4, though.
Yes.
Not for homework 1 through 3. Okay. You still have to write them out. Muscle memory, right? Okay.
Actually, one of the with regards to submission, do you prefer paper or LaTeX? I think I'm using that a lot.
Well, cool thing about LaTeX is that you can print it.
Yeah.
I think probably just print them out. Like I typically do like very digital classes, but I haven't been doing a lot of that in this class. It's been a lot of paper. So I assume most people are going to hand in written stuff, and it's easier for me to keep track if it's all in the same medium.
Okay.
Like if some people turned it in electronically and some people turned it in by paper, I'm going to lose half. I can't tell you which half, but half of them are going to get lost. Okay. So throughout the book, they use geometrized units. So just be aware of that. If you actually want to calculate anything in CGS or MKS, you got to find your constants, right? Which Thorne and Blandford talked about. They've got that nice section where there's a nice table telling you how to put back in non-geometric units. The other notational difference is that Latin indices go from 0 to 4. I'm sorry, 0 to 3. C versus Fortran gets me every time. So this is different, right? So for instance, GAB would be the 4 metric in Baumgart and Shapiro. In Thorne and Blandford, they use Latin indices for just spatial, right? For 3 vectors and 3 tensors. But here in Baumgart Shapiro, they use A through K, something like that, for 4-dimensional stuff, and then I through L or something like that for not I through K. Anyways, A, B, C, D, E is going to be 4. I, J, K, L, M, N is going to be 3 in Baumgart Shapiro. Does that make sense? And so, if I just wanted the spatial part of the stress energy tensor, that'd be that, which is the spatial part of TAB. Slightly different notational difference. The reason they do that will become more apparent when we start talking about the 3+1 decomposition. The reason they do that is that they are going to treat this thing as what they call abstract index notation, which is the same as slot naming index notation in Thorne and Blandford. Okay, so in other words, this is not the components of the metric, but this is the geometric object, the metric, right? And so they will almost never do the boldface stuff, which makes it much easier for me writing on the board and much easier for them writing on the board because this is just their lecture notes they put into LaTeX form. I happen to know. So that's how they represent slot naming index notation. You'll almost never see the boldface stuff. Sometimes they will use it to emphasize the fact that they're talking about a geometric coordinate-free object. Now, when they do talk about components, they will often use Greek indices. Okay, so when they actually mean the components of the metric, they'll do G alpha beta when they're talking about components. Okay, so that is a notational difference to look out for and not get tripped up by. Okay, most of the time, as you're reading through the book, you will see that it is clear from context what they mean when you're looking at this stuff. Okay, and again, this is the abstract index notation. Through the first chapter of the book, really, they're kind of loose with that. But as you've already come to appreciate, there's very little distinction in most situations between the components of a geometric object and its abstract index notation or its actual geometric coordinate-free representation, unless you're doing something very specific. Okay. The other thing that is different is their use of terminology, basis one forms. Okay? So we didn't talk about one forms in Thorne and Blandford, not by name, but we were actually using them. You just didn't realize it. So a one form is the thing that is dual to a vector. So a one form is a covariant vector. Okay? So if I were to talk about a one form, let me call it V sub A. That looks like a vector, doesn't it? It's a rank 1 tensor. And in particular, it is a real valued linear function of one vector, which is another way of saying a rank 1 tensor. This you might call a covariant vector, which is a one form. As opposed to this, a contravariant vector, which is what we call a vector. Now, if you'll recall, in most Euclidean flat space scenarios, didn't matter. So we usually don't have to make a distinction. But when we finally got to GR, we did have to make a distinction between upstairs and downstairs, right? In Thorne and Blandford, we just called it upstairs or downstairs. Contravariant components versus covariant components. They didn't use the word one form, but they did use the mathematics. So throughout the book in Baumgart and Shapiro, you will see them using the terminology one forms and basis one forms. And so these things are dual to each other, right? And I didn't write this down in my notes, but just to remember, duality. So one form is dual to a vector. So what's this equal to if these things are dual? Delta function, AB. All right. So they are dual to each other. Obviously very intimately related, but they're technically different geometric objects. And we have basis one forms then, which will be denoted by omega with a tilde on top. And then let's see what's the notation that they're going to use here. And alpha upstairs. So those are the components then of this basis one form. And that is then dual to the basis vector E alpha. That's the notation. So this is a basis one form, which is dual to the basis vector and components thereof. And so you can use scalar product of one forms. Do the following. So if I've got some vector one form dotted into some other vector one form, right? Really, I shouldn't say vector one form. I just mean one form, right? Just like for vectors, we're going to do that this way, right? Now here I'm representing this one form as that. And you remember we could represent any vector as the components of that vector multiplied by the basis vector, right? And so in an exactly equivalent way, this one form A is its covariant components times the one form basis vector, the basis one form, right? Totally analogous. Same deal here. B, sorry. Alphas and A's are going to get me until I get used to Baumgart and Shapiro. So bear with me there. Okay? Same deal there. We've just redefined what a one form is. And in then this notation, I would use the metric, but now the contravariant metric where GAB is just the inverse of the usual metric GAB. So again, we're just taking everything upstairs, right? We're making what was covariant contravariant, moving on with our life, but now we're giving it some terminology and a little bit more mathematical rigor, which will be important. Okay, also this duality relationship, I'll just stick this up here because we already sort of said it, but omega, one form, dotted into basis vector, again, has got to be our delta function, delta A, B, for the basis vector and the basis one form, if those two things are dual to each other, right? I even screwed up the alpha here. I'm sure that should be an A. This is going to get me for a little while, so just bear with me. It doesn't matter in this context, obviously, but the switch from Greek to Latin is going to get me. Okay. The scalar product of a one form and a vector does not involve the metric, which is another very convenient aspect of one forms and vectors. Okay, so if I were to take vector A and dot it with one form B, I would have EAA, EA, that's my vector A, dotted into BB, basis one form, oops, upstairs B, like that. That doesn't involve the metric then. That is just going to be A delta A B B B. Did I do that right? Nope. Switch them. Like that. And so that's just going to be equal to A B A, right? That delta function transforms the B into an A, or if you'd like, the A into a B, either way, right? And so this is what you might call vector contraction, right? If you see that terminology around. We're contracting on those components, right? And so they'd go away via the Einstein summation convention, right? Okay. Now, the one form and its vector carry the same information. So one form and the vector that it's dual to carry more or less the same information, but in different ways. Okay, and they're related in the way that you might expect, which we're used to from already from Thorne and Blandford, which is just like this, right? So this is my one form, this is my vector. And in order to get the one form from the vector, I just use the metric to lower the index, right? Thorne and Blandford talked about index gymnastics, raising and lowering. They elided over this terminology of one form. But you've seen this, right? You just saw it. You just didn't realize you were seeing it at the same time. Same deal here, right? If I wanted to get the vector from the one form, I'd use the inverse metric, G upstairs AB, to get that. All right. You can have a coordinate basis of one forms. In that case, we have our omega A, which is equal to some vector, well, actually one form, displacement in some coordinate basis. Analogous to our, completely analogous to the basis vector, right? But now the indexes are upstairs instead of down, right? And this would be for some set of coordinates XA, right? Like that. All right. And you can have orthonormal in the same analogous way, but now we're dealing with one forms instead of vectors. And we're going to represent orthonormality with the caret on the index, just like we did in Thorne and Blanford. And so then if this is orthonormal, and I'm dotting those two basis 1 forms together, what do you guess that I get when I dot product those two things? Or the flat metric, right? Or the flat metric, right? Which I'll represent like this, with our little carets, indicating that this one form basis is coordinate and orthonormal. Okay. Okay. So an interesting thing that comes out of this, which again, Thorne and Blanford kind of skip over a little bit without putting it right in your face, is that the gradient of an arbitrary scalar field is actually a one form. The gradient of an arbitrary scalar field is a one form. We treated it like a rank 1 tensor, which a one form is. But so here you go. So I could say that the one form gradient, which I'll represent like that, is just dA, partial A of f. The scalar field is f. Some one form basis like that. This is starting to go. Okay. So the components of this then are the ordinary partial derivatives. And then in this lingo, and some of this is now just review, just so that we write down the notation that Baumgart and Shapiro are using. Okay. Directional derivative. I spelled that wrong. Derivative. In this notation, so we would take some vector, now that is a vector, and dot it into the one form gradient, right? And that would be VA, and now this is a vector, so I'm using a basis vector, dotted into my definition for the gradient up there, partial derivative of the scalar field using my basis 1 forms, like that. And then in the end, this is just VA partial A F. Because of the duality. Okay. Basis transforms, much the same way, using a transformation matrix, right? And so if I wanted to take, well, we already know this, but just to recall, I'm transforming the basis vector EB into EA prime. I would use some transformation matrix M, like that. And we had the transformation matrix before. And I can do the same thing with the basis 1 forms. Omega alpha prime is going to be equal to MA prime B with the basis 1 form B. These two matrices are the inverse of each other. Again, like I think we did this in Thorne and Blanford. It just wasn't called one form. Okay. These things imply the following, which is my vector A prime is this. Yes, right? To transform a vector. Transforming a 1 form, I'll call it B. Transforming a one form, very similar, but now I'm going to use, actually I'm going to, the ordering doesn't really matter, but when you're working with one forms versus vectors, this is just a convention to change the ordering of what goes where, but it doesn't actually matter mathematically. It's just a convention. And so I can transform one forms using the inverse of that transformation matrix between A prime and B, my two different sets of coordinates. Going a little fast through this because it's mostly review and I just want to refresh us and put it in the lingo of one forms. Okay. All right. Okay. The extension to higher rank tensors is kind of straightforward. So just say higher rank. You'd have something like this tensor object now, bold T. I can represent as its components A and B, E, A, and one form B. Okay, so now this is a mixed component tensor. It's got some upstairs, it's got some downstairs. And if I wanted to express that geometric object, I would use both the basis vector and the basis one form, along with its components, the upstairs and the downstairs components, to represent that geometric object. That's how that would work. Okay? And obviously, these two things next to each other like this are a tensor product, right? So this thing here is second rank. This is, well, the second rank components. So you get a second rank tensor. Okay. Same deal with transformations. I would use, for instance, the two different transformation matrices. If I wanted to transform from A to B to A prime, B prime, I would have a transformation matrix from C to A prime, put in my tensor, TCD, and then on this side, I would have going from B prime, from D to B prime. The ordering doesn't actually matter, but this is just convention to put them on those different sides for those transformation matrices. Okay, now we can define the covariant derivative in this lingo, which measures the change of a tensor with respect to parallel transport. Okay, so we use this essentially to define parallel transport, but this is telling you how this tensor is changing if you parallel transport it, right? It's the gradient. But technically it's the covariant derivative, okay? So we can write this down as nabla A, B, right? That's how we're going to express this. Again, this is the gradient, right? But formally, technically, specifically, it's the covariant derivative. And we can express that as partial C TAB plus, here comes our old friends, the connection coefficients, DC, TD, and B plus, I'm sorry, minus the connection coefficient D, BC, TA, D. Like that. Did I get that right? Yeah. Just collapse in the right way to end up with mixed component TAB, right? And so in flat space, the connection coefficients are 0, and you just end up with the gradient as the partial derivatives in the different directions. Just like we had before. Same deal. Same deal. Sometimes in Baumgart-Shapiro, you will see this notation. Do not be alarmed. Doesn't mean anything except that they specifically mean there that this is the four-dimensional connection coefficients. They'll sometimes use that notation to be very clear about whether they mean 3-dimensional or 4-dimensional. Sometimes they use it for 2-dimensional, right, if you're projecting down onto a 2-space. So if you see that notation, they just mean the 4-dimensional connection coefficients. In a coordinate basis, what are the connection coefficients called? Pop quiz. Yes, the symbols.
Christopherson.
Christoffel symbols, yeah. Good. Sure you stay frosty. Okay. Oh, and as is obvious by this notation, right? Taking the gradient increases the rank by 1, right? Because none of these 3 indices are summed over, right? None of them are contracted. And so I've got 3 free indices there, so it's a rank 3 thing. Right? Okay, so that's pretty much the review of notational stuff. Any questions about that? Again, 1 forms are just upstairs vectors, which is all Thorne and Blanford did with them. We didn't go much further with that. But since we're going to get hot and heavy into the numerical relativity stuff, they're going to use that terminology and the specific mathematical machinery of it. So I thought we should review it. Now let's talk about black holes. More fun. Black hole. I will often abbreviate this, especially if you read my notes, just as BH. Black holes. So this is, okay, let's do this. One of you give me what your definition of a black hole is. What's a black hole, Oliver? Yeah, absolutely. That's the good, rigorous definition of what a black hole is. It's some region of space-time that cannot communicate with the outside. Can't get information out, right? And what is that black hole bounded by? What do we call that? The event horizon, right? That's the three-dimensional, the 3 surface that bounds the 4D object of a black hole, right? And that's sort of the wall shielding the black hole from the rest of the world, okay? So it is region of space-time that can't communicate. With the outside universe. Right? And it is bounded by a surface, a 3 surface, which we will call the event horizon. Alex, you got that red marker?
Got it right here.
We're going red.
Ready?
Yep. Ooh, thank you. Okay. So it's causally disconnected. And in the center, formally, oh yeah. Ooh. I'm screaming at you now. Woo! That's right. Disconnected singularity forms in the center. Now this is kind of fun. So this is formally, mathematically, and physically a singularity. It is a region of infinite density. All of the mass of a black hole resides at the very center, at least for plain vanilla black holes. And that's kind of interesting because the equations of GR admit this, but we know that it's fundamentally in tension with quantum mechanics, right? Like, and anywhere that you see an infinity in your mathematics for physics, you usually have alarm bells going off, like, you know, there be dragons. And it's true in this case. We know that there's fundamental inconsistencies with black holes and quantum mechanics, which was one of the things that makes them so darn interesting. Because we know that GR admits the solutions that describe black holes. We also know they exist. We know black holes are real. And you know, you guys, you kids these days, you take that for granted. But you know, when Carl Schwarzschild wrote Einstein a letter, it was like, hey man, cool equations. I found some black holes. People didn't buy it, right? People didn't think something like this could exist. But they do. So the general solution, completely general solution for the black hole metric. Okay, so the space-time metric that describes a black hole is called the Kerr-Newman metric. Okay, and it describes a black hole in complete totality, right? Total arbitrary everything about a black hole. And do you know how many free parameters it has? How many free parameters do you think it describes to completely arbitrarily describe it? 3? Yes, that's it, right? 3 parameters, what are they?
Angular momentum, mass, and charge.
That's it. Spin, mass, and charge. A black hole can only have 3 properties. Those 3 things describe everything there is to know about a black hole. So really, they're pretty simple objects. John Wheeler was famous for having said black holes have no hair, right? They have, that's it, right? They're not interesting. They're not complicated. They've got 3 parameters, right? They have Q, charge. They have J, angular momentum, slash, you'll often hear this spin, and M, mass. That's it. And here's the thing. How important do you think this one is? Not really, because the universe is pretty much charge neutral as far as we know, right? And so the black holes, by and large, we think should be charge neutral. And this is true, right? There's no way to form a charged black hole, at least physically that we know of, right? These come out of physical processes of the evolution of the universe and the stars. They're gonna form more or less charge neutral. But fun thing, if you spin one of them, you can anything that spins and has a magnetic field actually has slight charge separation, which can lead to a very, okay, I'm getting off the rails here, but it can lead to a very minute charge of the black hole, formally speaking. We're talking 1 part in 10 to the minus 4 kind of thing, right? But technically, it can matter. And so even for black holes that we would treat as being charge neutral, if they have a magnetic, if they rotate, they spin, you can lead to charge separation. So anywho, there are special cases for black hole metrics, which you have probably heard bandied about, because I know we all talk about black hole metrics all the time. Okay, so special cases of black hole metrics, which we will encounter. Q equals 0, which is a pretty common one, right? This is the Kerr metric. So this is a black hole that has mass and spin. J equals 0, so it's a charged one, but doesn't have any rotation. You will rarely encounter this one, but for completeness, here it is. It's the Reisner-Nordstrom metric. And then finally, Q equals J equals 0. Anyone know what this one's called? The Schwarzschild. This is the Schwarzschild metric. Here we go. Schwarzschild. That is a lot of consonants next to each other. All right, so that's the Schwarzschild metric. And this is the one that, like, you guys know the story behind this. I'm gonna get something wrong about it because I didn't think about this until just now. Karl Schwarzschild, literally, he got, you know, Einstein had just written down general relativity, presented the papers on it in 1917. This was during World War I. Karl Schwarzschild writes from the German East Front. He was a soldier. Got this, wrote down the solutions, he found the first analytic solution to the field equations. And they were the Schwarzschild metric for a black hole. I mean, not long, months, not even quite a year after Einstein had presented the paper. And he did this from the Eastern Front during World War I, and wrote a letter, you know, to Professor Einstein, check this out, or whatever they said back then. So it's kind of an amazing story, and it's an extremely useful solution. One, you know, It's one of the first analytic solutions to the field equations. But also it describes pretty well most black holes. All black holes spin. And so by and large, you're going to see more commonly for detailed calculations, the Kerr metric, which wasn't until like 1960 something. Actually, Roy Kerr was working at my alma mater, University of Texas at Austin, which is also where John Wheeler was at the time. I wasn't though. But the Schwarzschild one we're going to use a lot because it's simple. Fact. Let's do that now. Let's write down the Schwarzschild metric. All right, I'm going to save myself, and I'm not going to write Schwarzschild again. Okay, so in spherical coordinates, we can write this down as follows. Like most cases when we're dealing with metrics, we will simply use the line element as an abbreviation for the metric because it's convenient. So ds squared minus 1 minus 2m over r dt squared plus 1 minus 2m over r inverse dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Okay, so this is in complete generality in full 4D the Schwarzschild metric, right? You notice that the black hole only does anything in terms of deviating from flat space to the time and radial components, right? So in the theta and phi, that's just a flat space metric, right? We're used to that from just plain old Euclidean spherical coordinates. So it's only in these 0 and 1 components that we see any change due to the fact that there's a black hole surrounding us, right? Or somewhere near us. So I shouldn't say surrounding us. Specifically, this is the metric outside of the black hole. So this metric actually describes only conditions in vacuum. All right, so there's some black hole at 0, at r equals 0, there is a black hole. We are outside of that black hole, is specifically what this applies to. If you have some amount of matter surrounding you that is gravitating, you have to have a more general metric, which hopefully we will get to today. Okay, R, we're going to call the areal radius, because it is the radius that defines the area of this black hole, specifically for some area A. We're going to define this radius as that A over 4 pi to the 1/2. Now you're going, well, duh, but we're not in flat space anymore, right? This is a Euclidean relationship. And so we have to make this distinction technically. But this is then a special coordinate. By choice, this is a special coordinate. Okay? So this applies to, like I already said, applies to vacuum. Specifically for r greater than 2m. That's because 2m is the radius of the event horizon in these coordinates. Okay? So this is the Schwarzschild radius. SCHW blah, 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 radius of the black hole. And again, geometrized units. So if you're confused, remember, mass is length. The sun weighs 1.5 kilometers. All right. Well, and that's where this comes from, right? For the sun. Okay. I won't even write this down because I can just say it in words. So if you look at this, there's symmetry in both time and the phi direction. And so there's killing vectors for both time and phi and associated conserved quantities. Remember killing vectors that arise from symmetries in metrics. And those conserved quantities are the total energy and the angular momentum. that are associated with those killing vectors. Okay. Okay. Around this black hole, we can have circular orbits down to r, actually, should I say equals? I should probably say equals, yeah. R equals 3m. So there can be stable circular orbits down to that radius. In between 2m and 3m, you can't have circular orbits. So if you ever hear the term ISCO when talking about black holes, that is the innermost stable circular orbit. For a short shield black hole, that is 3m. Okay. Oh, I'm sorry. No. I got that wrong. I skipped ahead in my notes. So you can have them down to 3m, but they're not actually stable at 3m. Sorry. I jumped ahead in my notes, but let me get there correctly. Okay. Okay, so here we go. So if our particle orbiting this thing has mass, I'm going to call it mu. So we've got some little test particle orbiting our black hole with mass mu, and it's in a circular orbit around our black hole. Its energy over its mass squared is equal to r minus 2m mass of the black hole squared all over r times r minus 3m. That's the energy of that orbit or that particle going around the black hole. And since it's orbiting, it's going to have some angular momentum L. Both of these are conserved quantities because of the killing vectors and the symmetries of the metric specifically, like that. So what you see is for a particle of mass mu at 3m, the energy goes infinite, right? So if that particle comes all the way down to 3m, the energy is infinite. That's what we would call the photon orbits. They're infinite energy orbits, and so no massive particle can do that. The only thing that could do that is something that is massless. And so particles, photons, can orbit a black hole at 3m.
So,
Yeah.
This is the orbital energy.
This is the orbital energy. That's correct. Correct. And angular momentum of the orbit. Okay? So at r equals 3m, the energy is infinite, all right? And those would be called the photon orbits, because only massless particles could do that. Okay? Now, for a massive particle, let me correct myself from earlier. The innermost stable orbit is actually at r equals 6m, not 3m, but 6m, for a stable circular orbit for a massive particle. Around a short shield black hole. Okay. Now if you, I erased the metric. I shouldn't have done that. All right, I'm going to write up the most important parts. I shouldn't have erased the metric. That was silly of me. Minus 1 minus 2m over r dt squared plus 1 minus 2m over r to the minus 1 dr squared, blah, 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 and the rest of it. If you look at this, there is a coordinate singularity. at r equals 2m from that term, right? That is nothing but a coordinate singularity. That's the radius of the event horizon, all right? And by clever choice of coordinate transformation, you can get rid of that singularity, like we do so many times in other areas of physics, right? Oops, coordinate singularity, let me transform my coordinates, it goes away, right? So you can get rid of that. And that means, with this metric, you can describe things that are going on in and around the event horizon, just in different coordinates, okay? But now, the singularity at r equals 0 is not a coordinate singularity. That's a real singularity. You can't get rid of that one. That is a physical singularity. And the way to see that, right, to prove that that's physical, quote unquote physical, and not just a coordinate transform or a coordinate singularity like the event horizon, let's consider the curvature invariant. I'm going to start this over here so that I don't get too crowded. The curvature invariant is just the scalar that you can make from contracting all the components of the Riemann curvature tensor. Curvature invariant. Being a geometric object, of course, it is invariant. Okay, I'm just going to call it I. I'm going to define it as Riemann curvature tensor ABCD, Riemann curvature tensor ABCD. So I'm contracting all four indices of the Riemann curvature tensor. In this metric, if you go through the mathematics, left as an exercise to the reader, that ends up being 4m squared over r to the 6th. So at the center, at r equals 0, that is indeed infinite. And so that means that the curvature of space-time at that point is infinite. That's what that means. And so in the context of GR, that's what a real singularity is. It's a point of infinite curvature in space-time. Okay. All right. Can I repurpose some of this? No, I can't. All right. Plenty of time. Let's move on from Schwarzschild black holes to the Kerr metric black holes. So now we're going to add rotation to the mix. Okay. To describe this, we're going to use a special set of coordinates called Boyer-Lindquist. All right. And that is, I'm going to start further over. It's going to get big. ds squared, our line element, is minus 1 minus 2mr over sigma, which will be defined in a minute, dt squared, minus 4a mr sine squared theta, all over sigma, dt d phi, plus sigma over delta, to be defined in a minute, dr squared, plus sigma d theta squared, and I'm not going to have room for this term, plus r squared plus a squared plus 2a squared mr sine squared theta, all over sigma, close parentheses, sine squared theta d phi squared. So a bit more complicated than the Schwarzschild metric, took from 1917 to 1960 something. 50 years, let's call it almost, to allow black holes to rotate, right? To figure out how to describe rotating black holes.
I wish I could remember this story too, because it's good. Roy Kerr, you know, like he was working on this at Texas. He was either a grad student or a postdoc. You know, and he was a chain smoker, just locked in his office, smoking indoors, working on this until he finally found it. Said something memorable. Okay, so let's define these various things which I've written up here with that explanation. So A is going to be defined as J over M. That's the spin parameter, okay? Where J is the angular momentum. Delta is going to be defined as R squared minus 2mr plus a squared, like that. And then sigma is defined as R squared plus a squared cosine squared theta. Okay? So if you take a look at this, if you stick in a equals 0, it reduces to the short shield metric, which is good. We better recover that limit, all right? You can convince yourself of that. The other thing is that there are limits on the spin. So I'll put it right here. So the spin parameter must be between 0 and 1 when divided by mass. So usually, you know, if you hear about folks talking about spinning black holes, they'll quote spins just in absolute numbers from 0 to 1. And that's a spin 0.9 black hole. That's what they mean in terms of the Kerr metric, this definition. Yes, both limits are possible. You could have a maximally spinning black hole at 1, and then obviously non-rotating black hole. Both limits are admissible. Okay. So obviously this is a little bit more cumbersome to work with, but not bad for describing so fairly high degree of generality a black hole. This also has, so like the short shield, due to stationarity and axisymmetry. Right, so I skipped over this explanation with short shield. But if you look at the terms of the metric, the components of the metric here, t doesn't appear, right? Coordinate time doesn't appear as a dependency anywhere. Neither does phi, the coordinate there. So same deal with the short shield. That was also true there. It's also true here. That's what I mean by symmetry. So it is symmetric in time, meaning it doesn't depend on the time coordinate. In other words, stationarity, right? And it's axisymmetric, meaning it doesn't depend on the phi coordinate, right? There is no dependence of this metric on phi or on t. So that's what I mean by stationary and axisymmetry. Two symmetries, therefore two killing vectors, therefore two conserved quantities associated with that. And all right. Again, same deal. Killing vectors, partial t, partial phi, the basis vectors in those directions. Those are the killing vectors then. And from those come conserved quantities of total energy and angular momentum. Okay. Oops. The black hole horizon, in this case, it's a little bit more complicated than the short shield. What you do is you set delta equals 0, this guy, and you take the largest root.
And from that, you get the following, which we'll call R plus, which is the biggest root of this equation here, is R plus is equal to M plus M squared minus A squared to the 1/2. What do you get if you make A 0? 2M. What's the short shield radius? 2M. So it reduces the short shield. But that's the radius of the event horizon for a short shield, or a curved black hole that's spinning. What do you get if A is 1? Yeah. Yeah. So 1M, right? And so a maximally spinning black hole will have a more compact event horizon. It won't be spherical though. Okay. Okay. I think that's good for that. Other questions about curved black holes? There's a few other details. You should go back and just read chapter 1. I mean, it's a quick read. I am skipping over some details, and if any of this is not completely clear, how could it not be, right? The book has some interesting details. As we go along through the semester, though, we will come back to black holes. But this course, we won't cover all the nuance of GR with regards to black holes. But we will do some solutions numerically for black holes. Okay. This is fun. So let's talk about this real quick, and then I need to get to TOE. Yeah, 5 minutes. We're going to do 5 minutes on this, and then we got to go to TOE. Global theorems for black holes. So there are the 4 laws of BH dynamics, mechanics, let's call them. I won't write them all down, but they're actually analogous to the 4 laws of thermodynamics. And so it turns out that black holes, while being very simple objects described just by 3 numbers, behave very much like thermodynamic systems, right? These mechanics, the laws that govern their sort of behavior and evolution, are very analogous to just the laws of thermodynamics. In particular, the second law. So the second law of black hole mechanics says that in an isolated system, the sum of the surface areas of all black holes is preserved, is constant, is a conserved quantity. The sum of all the surface areas of all the black holes doesn't change. Cool, right? So I actually don't, huh?
Like every black hole?
Like in an isolated system, right? In an isolated system. Now, isn't that weird? Yeah.
In the universe, there has always been the same surface area of potential horizon.
Is the universe an isolated system?
If we're talking about the entirety of it, I would think it is.
I'm actually not 100% sure of this, but if the universe is infinite, it might not be true. If the universe is infinite. But if the universe is not infinite, then yes. And there's caveats here, okay? So there is an irreducible mass for a black hole, and that can't change. And so classically, this mass of a black hole can never decrease, classically. And so from a classical perspective, that's how you satisfy the second law of black hole mechanics. But now we know from Hawking, right? From Hawking, that black holes radiate. I won't get too deep into this one, but I'm sure you've all read A Brief History of Time or whatever, right? So you understand the combination of event horizon plus quantum uncertainties means spontaneously creating particles right at the event horizon. One could fall in, one could go out, right? Therefore, since the event horizon must be quantum uncertain, the black hole can actually lose mass. And it can radiating. And more than that, black holes have entropy. And that entropy is very much related to their surface areas. And that entropy is S is equal to K, the Boltzmann constant, C cubed over GH bar, area of their event horizon over 4. So it's a bunch of fundamental constants, and then the area of the black hole. So the entropy of a black hole is the area of its event horizon, right? So going back to the second law, if I have an isolated system, that total sum area cannot decrease. So accounting for Hawking radiation, the generalized second law would say that the total amount of black hole entropy cannot decrease. Again, analogous to the second law of thermodynamics, entropy must always increase. So for a black hole, its surface area is its entropy. And so for all black holes in an isolated system, that entropy can't decrease. So the thought experiment, at least that I did, I think the book doesn't do this, but imagine that, what do we do with thermodynamics? We always have a black body, right? You put everything into a box and then ask what happens. So put a bunch of black holes into a box, right? With perfectly reflecting walls, let's say. So I'm isolated from everything else out inside the universe. Now imagine these black holes can indeed radiate, right? They can lose energy. And Hawking radiation would say that eventually they could evaporate, right? But now I've got all these black holes in here, they start to radiate, everything perfectly reflects off the wall. Every photon, or whatever it is that the black holes are radiating, eventually gets absorbed by some other black hole. And so since total energy must be conserved, the total sum area of all the event horizons in that box must also be preserved, right? Even in the case of quantum mechanical Hawking radiation. Okay, there are 3 other laws of black hole mechanics, but that one's kind of fun. Right. Now let's get to what we actually need for doing the project. Pullman, Oppenheimer, Volkoff equations. I mentioned this before. This is the general relativistic equivalent of hydrostatic equilibrium, but now we're admitting relativistic stars. And the metric for a spherical star it's going to look something like this. ds squared is going to be equal to minus e to the 2 phi dt squared, I'll define phi here in a second, plus e to the 2, that's a terrible 2 lambda dr squared, plus r squared d omega squared. Omega is going to be the solid angle that we're so very used to. So phi and omega are functions in general. They're functions of radius and time. Now, we will take the limit where they are not functions of time, meaning that we will assume stationarity, but in general, they could be functions of time as well. And then d omega squared is what you're used to. D theta squared plus sine squared theta d phi squared. Okay, just a solid angle. Okay, so there's our metric that we're going to use to describe a spherical star. And if it is static, phi and lambda will not depend on time. Now, to solve this, let's assume a perfect fluid. So a simple equation of state. Okay? And I'm going to have some mass energy density rho, which is equal to rho, a function of the baryon number density and the entropy of the material. right? So now I'm specifying this as the baryon number density because that's a conserved quantity, right? That's a conserved quantity. And S, this guy is the specific entropy. The specific entropy, it's just like, increasing the temperature, right? Increases the entropy. Okay, and we can get the pressure from the first law of thermodynamics, which would say that the pressure is equal to the baryon number density squared times the partial derivative of rho over NB with respect to NB, right? That's just first law of thermo for defining the pressure. So in other words, my pressure is also going to be a function of the baryon number density and the entropy, okay? So this reduces then just to a function of rho in certain cases. There's a few others, but so I can take the limit of zero entropy, which means cold, completely cold, which in your project you will do. That's what I want you to do in your project. Just assume cold. And so in that case, the pressure is only a function of density. And that makes this a far more tractable problem. It's almost analytic. Okay. So the GR equations of stellar structure, then, from this, we just need to define what phi and lambda are. We'll do that in a second. They are a set of coupled first order ODEs, which is pretty easy to solve, okay? I'll spare myself from writing that, I'll just say it in words. A system of coupled first order ODEs, okay? And what we need to do to solve that is define the metric function, which I'm going to call m of r, and that looks something like this from this definition. E to the lambda is going to be defined to be 1 minus 2m over r to the minus 1. Okay? So that's how we define this metric function, m of r. That indeed is going to be something like a mass as a function of radius. And now we've defined my lambda, which I can put in there. And then solve. Then if we take this metric, simplified by this, simplified by stationarity, and plug that into the field equations, so G mu nu equals 8 pi T mu nu, GAB equals 8 pi TAB, assuming this very simple equation of state so that I can define my stress energy tensor for that equation, I can come up with a set of structure equations then. I'm going to erase the metric because I don't think I need it anymore. Okay? And that set then of coupled ODEs is as follows. dm dr is equal to 4 pi r squared rho, which is where you go, duh, right? It gets more interesting though, I promise. dp dr, which is in the Newtonian case, very simple. Here is a bit more complicated. Minus rho m over r squared, all times 1 plus p over rho, all times 1 plus 4 pi p r cubed, all over m, metric function, all times 1 minus 2m over r to the minus 1, which I've written off the screen there. And then d phi dr is going to be minus 1 over rho dp dr 1 plus p over rho to the minus 1. So the way that I have defined my sort of coordinates by this metric function, which acts like a mass's function of radius, this looks very much like the Newtonian version, only this now is the total mass energy density, not just the mass density. Okay, so this sort of is why these variable choices were made, right? This now looks very analogous to the Newtonian, where we've now included mass energy, not just mass. And then the other equations, this is sort of like a gravitational potential, right, in a Newtonian context. It's setting the strength of gravity here. And then this is substantially more complicated. But it does reduce to the Newtonian limit if you take the proper limits of the mass energy being completely dominated by rest mass. Stick it in there, slow motion limit. There's no V in this at all, but P is small, right? So remember, the Newtonian limit not only requires that the mass energy density be dominated by rest mass, but that the stresses be low as well, right? The stresses be small. Another way of saying that is the P is small, right? And so you can then simplify these equations back down to their Newtonian variants. Pretty straightforward. And so these then are the Tolman-Oppenheimer-Volkoff equations. All right. A few other notes here. All right. Let's see. So this metric in this form, I can just say this out loud. It's written down here because I think I'll pull up the project that I want you to do now. So if you go outside the limits of this metric, basically where P equals 0 and where rho equals 0, that's the limit of this star, right? That's the edge of this star. If you go beyond that, you actually match smoothly onto the Schwarzschild metric, if you take a look at the metric that we had defined before. And so outside of the star, it's Schwarzschild. And then inside of it, it's described by that metric I wrote up on the board a few minutes ago. So that's good. And we can integrate the total rest mass. I've got that in the notes. But let me see if I can, real quick, plug in. Show you what I want you to do for the midterm project. It is essentially integrating these equations I just covered up, right? Given some equation of state. I run an HDMI cable. I'd be right here. Okay. I just thought of an amazing life hack. I could just sit up here and scroll through if I knew how to make this work. Uh-oh, I don't know how to make this work. Oh, it made me wait. It made me wait. I may have to extract. Oh, hello. Okay, so that's good. Aha. Oh, Eric, stop being smart. That would be much easier. I'm already logged onto this computer. Why don't I just bring up the website here? Now you can see that, right? Okay. So we're going to solve these equations. What I want you to do is write a simple numerical solver. You can do it in any language you want. I don't care. I do recommend if you know Python, do it in Python because you can use NumPy and do this really quick. Right? You just plug in some ODE integrator and you're done. At first, I want you to assume just a polytropic equation of state. P is equal to K times rho to the gamma. Okay? And then using that, I want you to find the maximum mass for a cold neutron star, meaning temperature 0, entropy 0, using these parameters. Gamma equals 2.75, and K of 3,000, which is unitless if G equals C equals M of the sun equals 1. And then the next step of that is you're going to modify it to input an arbitrary equation of state, a realistic table-based equation of state that's actually used for simulations of neutron stars, and compute the maximum mass for any old 5 tables that you like. So let me show you some things that will be useful for this. So these are sparse directions, but this set of notes will be useful. This is from a summer school that was taught at Caltech. So here is a little more explanation of the TOV equations than even what's in the book. But here's our metric, right, which we just wrote up there. Convenient thing here, G's and C's are written out. And for the sake of numerical calculation, you're going to like that. You're going to know where to put them. The other thing that the notes do, so there's the full set of equations then. And this is in non-geometrized units. This should be in CGS if you pick your constants correctly. And so this is probably a little more useful to actually getting numbers. When I ask you what's the maximum mass of a neutron star and you go 0.2, well, and that's not wrong in the right units, but I'd like to know what it is in solar masses. And so there you go. And then that's the polytropic equation of state that I want you to use at first. There's some other nice things in this note that we didn't go over that I want you to read and understand. Gravitational versus baryonic mass, they're not the same. Which do you think is more, the baryonic mass or the gravitational mass of a neutron star? Why?
Because there's energy in the neutron star and the baryonic mass. You would have to add the energy mass.
Is gravitational binding energy positive or negative for a bound object? Negative. So is the baryonic mass greater or less than the gravitational mass? Yeah, so the gravitational mass is slightly less than the baryonic mass. For a neutron star of like 2.5 solar masses, it's a couple tenths of a solar mass. So it's not a ton. But because it is a gravitationally bound object and binding energy is negative, it's slightly less massive gravitationally than baryonic, which means you would get 2 different numbers. If you measured its mass using gravity versus literally counting every baryon in it and going, okay, the mass of a baryon is, right? Here's a nice table for converting. It's very similar to the table in the notes from Thorne and Blanford. And then the notes even go through the numerical procedure of how to solve this numerically. This starts with a simple Euler method. I would like you to just go ahead and jump right in and do a high order Runge-Kutta method. You can play around with it if you want to. I mean, standard RK4, Runge-Kutta 4 is all I want you to use. You don't have to play around with that too much. Yeah, and so read these notes. I don't want you to do, like, this isn't the assignment. What the assignment is I actually think a little easier than this, at least at first, but these notes will help you understand what you need to do. The other thing then, which will be helpful, is I want you to use these,
Advanced.
Thank you.
Add exception.
Thank you. Oh, well, we're in the process of moving this website, so I don't know if that's maybe part of that. So on this web page, there are a whole bunch of tables for different tabular equations of state. And I want you to read these into your solver and use them instead of the polytropic relation, P equals K rho to the gamma. Use this to get the pressure as a function of rho. They're HDF5 files. And depending on what language you want to use, there are driver routines that will read them in Fortran right here. This actually, EOS driver, I think has both C++ and Fortran, or is it just C? I have Fortran if you want them. It's also very easy in Python. If you've used h5py, you're done. And then you use numpy.linterp. Is that the one? I don't know. There's a linear interpolation, a multi-D linear interpolator in NumPy. You're done. Because you're going to have to interpolate rho, pressure as a function of rho for these tables. The other thing I didn't think to put in the notes, which I'm just now thinking, well, I should let you go, is you'll have to worry about the electron fraction. Assume it's 0. Pure neutrons. Cold, pure neutrons. And so that simplifies this immensely. And, you know, get working on this, but I'm totally going to help you, especially with some of this, you know, technical garbage of reading in these tables. But I'd like you to compute the maximum masses for a few of these EOS tables. There's a bunch here. Pick whichever ones you want. I don't care. Does that make sense? All right. Let's get to it. Thank you, everybody.
Have the microphone, please.
Hopefully I didn't use it all.
That's okay. I was still from work.